Hi everyone, Miss B here again. Um, and in this video we are looking at the Unit 1, Lesson 4, Cumulative Practice Problems for Illustrative Math Geometry. This lesson was about construction techniques and constructing equilateral triangles. So let's start with this first question. This diagram is a straight edge and compass construction. A is in the center of one circle and B is in the center of the other. We want to explain how we know that triangle ABC is equilateral. So ABC is this triangle right here. We are trying to explain how we know that is an equilateral triangle. So first off, we're going to just do piece by piece with some of our segments here. So I know that AB is a radius of both circles, because these circles pass through each other's centers. And so that means that AB is the radius of both. And so the circles are going to be congruent to each other. So we're going to start with that and say um, AB, or segment AB is the radius of both circles, just to get that out there. And so we're going to take one circle at a time here. So looking at our first one, that's circle A, just because that's the one they named first. So AB, that's this one here, AB, that's a radius of circle A, and so is AC. So we can say that those are the same length. So AB is the same length as AC because they are both radii of circle A. And we're going to be able to say the same thing about two segments being the radius of circle B. So that's going to be BA, or AB, and BC. Oops, didn't mean to zoom out like that. So AB and BC are so the same length because they are radii of circle B. So that means that all of them are going to be equal to each other, basically. So I'm going to actually use some of the notation that we use to mark some things congruent. So we originally said, actually I'll do this in red so it shows up a little better. We said that AB is the radius of both circles, and then we said AB is going to be the same length as AC because they're both the radii of circle A. And then we also said that AB was going to be the same length as BC, since they're both radii of circle B. And so now I have one of those congruence marks on each side of this triangle, which means all three sides have to be the same as each other. Let's look at diagram number 2. So for this problem, it says A, B, and C are the centers of 3 circles. How many equilateral triangles are there in this diagram? So we have some options here. So highlight, outline, use colored pencils, etc. to show the triangles. So we want to number, but also try to show where each one is. So first off, I'm going to try to do the smallest triangles first, and I may end up using some additional highlighter colors here. I think I have a couple others, so I should have enough. Um, I see a couple, so if we just focused on circle A, I'm going to use well, I will highlight AB first. Um, we're going to use a triangle built off of this. So AD to DB and AB, those are all, for the same reasons, radii of congruent circles. So I have highlighted down here a yellow triangle. In a similar fashion, I'm going to have another one centered at A extending to H. And this triangle, we can also connect to A and C, and then C and H. So I'm going to try to color in here with my highlighter marker stuff on my tablet. So I have two equilateral triangles here. I have a third one centered at A that is sort of in the middle. It's going to use AC and AB as well as BC. So I'm going to switch over to a blue highlighter here. Hopefully you can tell the difference between these. I know sometimes highlighter colors are a little difficult to see. So we have this middle equilateral triangle. So all three of those triangles connect with the center of circle A. Likewise, I have three triangles that connect to the center of circle B. That's going to be the yellow one, the blue one, and then this one that I haven't colored in yet. So I'm going to pick a different highlighter color. So I have to select one here. Let's use, I think I have this pink color. I'm not sure how bright this is going to be, but this triangle right here is going to be one of my other triangles. So in total, I now have four, but there is one other triangle I have not colored in yet that I'm going to outline, because you might notice that these four individual triangles are all made from the radius of these circles. But I can also make an equilateral triangle out of the diameters of these circles. So if I look at the diameter of circle A, over here that extends from H to D, since all three of these circles pass through each other's centers, we know their radii are the same, which means their diameters are going to be the same also. And this big shape right here, this entire triangle, counts as part of it. So I'm also going to highlight, and I'll use a different color. Orange doesn't stand out too well. Let's see. Maybe red? Sure, we'll go with red just to show the exterior portion. So I'm not going to color over the whole thing because then it'll make it difficult to see, but that is 5 triangles. So we can say there are 5 equilateral triangles. And 4 of them are actually completely the same size and shape, and that 5th one is all of them together. All right, let's look at question 3. This diagram is a straight edge and compass construction. A is the center of one circle, and B is the center of the other. So now we are going to select all of the true statements, and then we're going to explain how we know for which statements we're selecting as true. So if we look at our first one here, I'm going to point a little bit with my laser pointer tool. This says AC is equal to BC. So AC is here. Is that the same as BC? Yes, that is going to be true. Both of those are radius of congruent circles because we have AB as a shared radius here. And so we have AB and AC as radii of circle A, and BC and BA as radii of circle B. So we are going to be able to say that, yes, these two pieces are going to be equal to each other. So we'd say, yep. And I'm going to put my little explanation and say they are, they're radii of congruent circles, or yeah, I would say they are radii of congruent circles, or equal circles. Congruent is the best word, though. So radii of congruent circles. Or you can say they're radii of the same length. Either way. So our next option here is AC equal to BD. So AC, again, a radius. BD, also a radius. But even though they're not connected at the same endpoint, they're still going to be the same length, because we know BD, or circle B, will have the same length radius as circle A. So this one is going to be true as well. So this would be, for the same reason, both radii of congruent circles, or what's a different way we can phrase that? We can say radius or radii of, we're just going to use the same phrase, congruent circles, radii of congruent circles. They're essentially both a radius at the same length. So now let's look at option C. This says that CD is equal to AB. CD is normally what we would call our perpendicular bisector here. And this was from our previous lesson. We learned how to construct a perpendicular bisector of a shared radius, like AB. Now, it's not going to be equal to AB. It will cut AB into equal parts, but it's not going to be equal to it, because from C to D is not a radius. It does not go from the center of a circle to the outside of a circle. It's going from an exterior point to an exterior point. So we are not allowed to say that this one is true. So I'm going to cross this one out. It now says ABCD is a square. Well, a square would have four equal sides, and this does have four equal sides, but it doesn't have four equal angles. A square has to have four right angles, and this does not, so it's not a square. Our next statement is E, that ABD is an equilateral triangle. So I'll use my highlighter tool to show which one they're talking about here. Maybe the green will show up. ABD. So they're saying that this shape right here at the bottom is an equilateral triangle. And this I agree to, because all of the outside lengths, or the sides of this triangle, are all radii. So this one is true as well. We can say all sides are, I'm going to say congruent. I'm just going to use this symbol to mean congruent, radii. And if you haven't seen it before, the equal sign with the little tilde or the squiggly or whatever you'd like to call it over top of it does mean congruent. So all sides are congruent radii. Now the last option here is F. So that says that CD is equal to AB plus AB. So they're saying that CD, our perpendicular bisector line, is equal to this radius plus this radius again. What that would mean is that halfway is the same as the radius. And we actually cannot say that that's true, because this point here isn't the center of one of the circles. In order to prove that something at this point is congruent to a radius, it needs to go from an exterior point, so from C, it then would need to connect to a center of a circle, so either A or B. So we cannot verify that it's actually this center point here, so this is not true either. And that is question 3. So now we're going to switch over to the back of this assignment or the next page. And we're going to look at questions 4, 5, and 6. So for question 4 here, we have line segment CD is the perpendicular bisector of segment AB. So they're giving us that this is the perpendicular bisector. So perpendicular, I know, means it makes 90-degree angle. Perpendicular means 90-degree angle, and bisector means it cuts that other line segment into equal pieces. So the question they're asking is line segment AB the perpendicular bisector of line segment CD? So they're giving us that CD is the perpendicular bisector, meaning that if we look a little closer at our diagram, what they've told us and what we know to be true is that CD makes this 90-degree angle, so that's true, and that it also bisects AB. Now, even visually, just looking at this, CD does not appear to be cut into equal parts. But even if they gave me something that looked like it was, there is nothing to tell me that those two pieces have to be congruent or have to be the same. So we're going to say no, because CD is not, we can say is not bisected or is not cut into equal parts. Is not bisected. I'm just going to also put in parentheses not split into equal halves. So it is possible for us to construct two lines that are perpendicular bisectors of each other, but in this case, they are not. So it does only work one way. CD is the perpendicular bisector of AB and not the other way around. Let's look at question 5. So question 5 here gives us 2 points in the plane A and B. So it's now asking us that so the first part of this question is asking, if we're only using a straight edge, can we find points in the plane that are the same distance from A and B? And to explain our reasoning. So can we use a straight edge? Well, a straight edge just allows us to draw straight lines. If we were using a ruler, we could try to measure and use measurements, but technically a straight edge, by definition, doesn't necessarily have those parts on it marking distance. All a straight edge tool allows you to do is to draw a straight line. So a straight edge and a ruler are technically two different things. So I would say for these, if I only have a straight edge, I cannot find points that are the same distance. I would actually need a compass tool in order to do that. So I'm going to write that. I'm going to say no. I would need a compass tool to find points that are the same distance. Okay. Now, part B says using only a compass can I find points that are the same distance away from A and B. So using only a compass, I can find points. I can't necessarily find all of the points that are the same distance away from A and B at the same time. But just to sketch it here, and I know that my sketching tools on this tablet aren't always super accurate, but we're going to try to draw a shape here, and make it as circular as I can. If I was to draw a circle all the way around here, let's see how, oh, no, that's going to be an oval. Not quite. We'll zoom out a little bit. Big circle. It's kind of going to make it a circle for me, but I'm going to have to move this a little bit. But what I would be able to do is take this circle, and if I made an exact copy of it, so let's do that actually. I'm going to copy it. And I can paste another circle here, and if I dropped this circle centered at B, I would be able to find 2 points that are the same distance away from A and B without using a straight edge at all. I actually can find the 2 intersection points here. So, yes, I am able to. I'm just not able to find the set of all of them. That would require using a straight edge to connect those 2 intersection points. And that would be our perpendicular bisector. So let's put some words to that. We would say, yes, we can construct circles centered at A and B that pass through the other point. And normally I would write this in a little bit more detail. I just don't have a ton of space on this actual assignment. So I'm writing it in a little bit shorthand instead of saying construct a circle centered at A that passes through B and construct a circle centered at B that passes through A. So I'm shortening that to just be this one phrase. We can construct circles centered at A and B that pass through the other point. And that's what I have in my diagram above, or what I tried to show. So through the other point, I'm going to make that a comment actually. And the intersections are the same distance. From A and B. Okay, so needed to actually draw a little bit on there. Unfortunately, my circles do go over A and B just a little bit. Well, of course they go over A and B. What I meant is they go over the question for portion A a little bit, but I hope the visual helps you understand what I mean when I'm describing it in words. All right, now question 6 is a different diagram, but it does say that, again, it is a perpendicular bisector. because this is from our previous lesson. So in this diagram, line segment CD is the perpendicular bisector of line segment AB. So CD is the long one that I have highlighted here with my laser pointer tool. That's the perpendicular bisector, and it cuts AB right here in half. Assume the conjecture that the set of points equidistant from A and B is the perpendicular bisector of AB is true. So that is a mouthful of a sentence. We are saying assume the conjecture that the set of points equidistant from A and B is the perpendicular bisector of AB is true. So this portion in red, we are assuming that is true, meaning that every point on CD is going to be the same distance away from both A and B. So now we want to select all statements that must be true. But I like to add things to my diagram first that I just know, because then that helps me with actually deciding which pieces could be true. So because they told me it's a perpendicular bisector, I am very happy to see that I have my perpendicular symbol here, meaning it makes a 90-degree angle. But they also said it's a bisector, so I'm going to include that AM and BM should be the same length by using those markings. Okay. Oh, and look at that. AM equals BM is actually our first option. So conveniently enough, this one must be true. If that conjecture is true, right? Then M would be that midpoint and they would be congruent. Now, what else needs to be true here out of these statements? So let's look at the next one. It says that CM is equal to DM. CM is equal to DM. Well, that is part of my perpendicular bisector, but we don't actually know if this piece is cut in half. This is the part that does the cutting, but it doesn't mean necessarily that it is itself also cut in half. So since we're choosing ones that must be true, we can't select that one because it's possible, but it doesn't have to be true. Let's look at option C. So this one says EA is equal to EM. So EA would be from this point to A, and then from E to M. Now, while they look like they could be the same distance, again, we don't know anything or we're not given anything specifically that means it has to be true. So we don't know that that's true. D says that EA is less than EB. So EA is the distance from E to A, and EB is the distance from E to B. Now, this is one that we do actually know is true. We know that that's true because if E was actually here instead on the perpendicular bisector, we're assuming this would make the distance between that and A and B the same. But because E is actually on A's side of the perpendicular bisector, it means it's going to be closer, and closer means that that value is smaller. So we are allowed to say that EA is going to be less than EB. It's another way of basically saying it's closer. Okay, so let's look at option E and then F. So option E says AM is less than AB. AM, is that going to be less than AB? Yes, this actually has to be true unless that entire segment had a length of 0. Because we know that AB is cut perfectly in half, we know that AM literally has to be half of this distance. So half of a number is always going to be smaller than that whole number, unless you're talking about 0, and this is not a 0. Now the last option here says AM is greater than BM. They are not greater than or less than each other because they are equal. And that was actually the first option we chose. So F is not true. It just isn't. Okay. So that's question 6. And we do actually have a little bit more on the next page. This homework assignment is a little bit longer, but there is more essentially review from previous lessons included in it. So here we have from the very first lesson of this unit, Unit 1, Lesson 1, a diagram constructed with a straight edge and compass. And our job is going to be to name all of the segments that have the same length as segment AC. So I'm going to highlight AC on here because that is the one that I am looking at to be the same length as. Now that's the radius of circle A. So I'm going to put a congruence mark there because now I can take any other radii of circle A and say that these pieces are congruent to each other. So AB, that's a radius of circle A. And if we ignored now circle A and just looked at circle B, AB is a radius of circle B. And circle B also has a radius here at BE. If I did that same process and ignored circle A and circle B and just focused on circle E over here on the right, I would see that there's also another radius here, ED, that is going to be the same as EB. So I can mark this one as well as a congruent piece. And we're just going to name all of those segments. So AC was our original one, so we're going to say AB. BE, and ED. Now, technically, you can name these segments from one point to the other because they are all endpoints. You could say EB or DE, and those would still be accurate. It would just be naming it in the reverse order, but it would still be correct. Okay, question 8. Get the whole question on the screen here. So starting with 2 marked points, A and B, we're going to describe the straight edge and compass moves required to construct the quadrilateral ACBD in this diagram. Quadrilateral just means 4 sides. So it's a shape with 4 sides. Quad means 4, lateral means side. So when we put it together, it's a 4-sided shape. So let's describe the straight edge and compass moves that we need here. That's going to start with the construction of our circles. So I'm going to say step 1, construct a circle centered at A and passing through B. My next step is going to be the same idea, but centered at B and passing through A. Construct a circle centered at B, passing through A. I have a little bit more room on here. don't want to cramp my handwriting too much. Now, we need to actually indicate points C and D. So we do have to include this as a step, that we're marking those points. So we're going to say mark the intersection of the circle, or the circles, um, as points C and point D. Okay, now our last step is going to actually just be creation of those four sides. So our job now is to construct or create those segments, and we would do that with a segment tool if we're using Desmos, or a straight edge in any other case. So we're going to say use a straight edge to construct segments AC, CB, BD, and DA. And those are the four segments around the outside. Looking at question 9 here, which is our last question, we have in the construction, A is the center of one circle and B is the center of the other. Which segment has the same length as AB? So since this is only a single answer question, not select all, I'm still going to highlight AB so that we can see which of the segments has that same length. So what we're looking at are a couple options here. So first they're talking about CB. So if we look at A, that says CB. Definitely not the same length. Not going to choose that one. Definitely not a radius, because AB is the radius of both of these circles. What about from C to D? This is also definitely not a radius of one of those circles. It goes from an outer edge to an outer edge. CE is also a segment that goes from an outer edge to an outer edge and is not a radius. So it is not C. And even though D is our only option left, we are still going to double check that it is indeed equal here. So it does ask about CA, and CA is a radius of circle A, just like AB. So yes, this one is going to be that. And we do have to put our reason. We can say A, B, and CA are both radii of circle A. And that's our reason. And that's it for this assignment. It is a little longer than our previous couple, but we had more things to review. So hopefully this helped you understand some of these questions, and I will see you in the next homework video.